that that's a little bit strange to be saying the second derivative and maxes and mins, because last time we talked about the second derivative told us about concavity, didn't it? Well, it turns out that you can use the second derivative, use the first derivative and the second derivative actually, but it's called the second derivative test because we're going to use the second derivative also to tell us about local maxes and mins. So we're going to use the second derivative to help us with maxes and mins. How do we do this? Well, here's the way it works. If C is a critical number of function f, C again is our critical number, where f prime of C equals 0, and the second derivative is continuous near C. So there are a few parameters here for this second derivative test, but this is how it works. Here's how it works. So we've got a critical number, and matter of fact, it has to be the critical number equal to 0. Critical number, not the critical number where the derivative does not exist. So that's special, and then you have to have the second derivative be continuous. You'll see why. But anyway, there's three parts to it. Three parts to the second derivative. A, if the second derivative at C, if that's greater than 0, then f of C is a local min. That's the A part. Let me talk about A part for just a second. So what we're doing is we're getting this critical number just like we did before, but then when we get the critical number, we're going to plug it into the second derivative of the function and see whether that's greater than 0 or less than 0 or equal to 0, but we'll talk about that later in a second. But if it's greater than 0, if the second derivative, you plug in your C value and it's greater than 0, it turns out you've got a local min there at C. Here's why. What this says is that if you've got the second derivative at C greater, second derivative does tell you about concavity. If the second derivative is greater than 0 at C, then what kind of concavity do I have? That's positive. That's concave up, right? So we've got concave up at C. Well, if I've got concave up, and we know it's a horizontal tangent, if you will, it's concave up at C. Here's C. Doesn't C have to be their low point? Because that's concave up. And so that's why your second derivative, if you evaluate it at C and it's greater than 0, it's a local min. Well, similarly, if f double prime of C is less than 0, then f of C is a local max. Because if I have the second derivative is less than 0, that's concave down, right? And so I've got concave down, which is more that shape, right? Concave down is like that, and so C being that horizontal tangent point, you've got to have a local max. And there is one other possibility, and that is if you evaluate at C the second derivative and you've got it equal to 0, what happens then? Then the test is inconclusive. Go back to first derivative test. Where you're checking, you got increasing and then it's decreasing or whatever. Okay? All right, so let's see a couple of these in action. This is all what's known as the second derivative test. Those three things there. And, of course, that part too. But all right, so let's do a couple. So instead of having to do the chart, we can do it this way. Let's see. Use the second derivative test for this. This one. Use the second derivative test to find the local max and local mins. Number 1. F of x equals x to the 4th minus 4x squared plus 3. Okay. Well, we're using the second derivative test, but we still have to find the first derivative. It's 4x cubed minus 8x, isn't it? But let's go ahead and do the second derivative as well. Be 12x squared minus 8. Okay? Go ahead and get both first and second derivative. But locating which values to possibly have local mins and max is still the same thing. How do we find we're looking for the critical numbers, right? And on the second derivative test, we're looking for the critical numbers where the derivative equals 0. So I'm going to start the same way, set the derivative equal to 0, and find my critical numbers. And so, critical number what would the critical numbers here be? Well, you got a 4x common factor, so let's pull that out. And so I get it. 4x equals 0, x squared minus 2 equals 0. So I got x is 0, x squared equals 2, so x is the plus or minus square root of 2. Okay? And so with the first derivative test, then we would have made our little chart here, but we're going to forego that and use this second derivative. So what do we do for it? So after that, when using this second derivative test, what we're going to do is then we're just going to look at the second derivative value at each of the critical numbers. For the second derivative test, look at the second derivative. Find f prime of c for each critical number. And let's see. It's basically the change here that we're doing. So f double prime of 0. Well, if I do the second derivative, now I'm evaluating the second derivative at 0. So I go to this one, plug in 0. At 0 minus 8, that is negative 8. Then I go back to my little table there, think about it. What that tells me, that's that second derivative at the critical number, and it's negative. That's concave down. So it's concave down. Negative second derivative is concave down. So what have I got at 0? Will be a max, okay? So the function value at 0 is a local max. Separate that out a little bit. Okay? All right, so do the same things. F double prime at square root of 2. Plug in the square root of 2 in the second derivative now. So we have 12 times the square root of 2 squared. That'd be 12 times 2 minus 8. That's 24 minus 8. That's 16. That's positive 16. That's concave up. So the graph has to be concave up at square root of 2. That's a local min. So f of square root of 2 is a local min. And then f double prime at negative square root of 2. Well, plug that in. Again, plugging in the second derivative. It's negative square root of 2 squared minus 8. 12 times that. Then minus 8. That's going to be about the same thing, isn't it? Negative square root of 2 squared. It's a positive 2 again. So that's still 24 minus 8. That's 16. So guess what? At negative square root of 2, so f of square root of negative 2, again, we have a local min. Okay? Kind of see how this works. It's just a different way of getting mins and maxes. Which way is easier? I don't know. Neither one of them is difficult. This one's a little more limited, I guess, but in usage, because there are some restrictions and things that come up. But anyway, that's it. Okay. Let's do one more. Second derivative test. All right, so same idea. Use the second derivative test, if possible. Hint, hint, hint here. Okay, so we just did. How about f of x equals x to the 5th minus 4x to the 4th? So same idea. Use the second derivative test to find the local maxes and min. Well, if I look at it, first derivative would be 5x to the 4th minus 16x cubed. Then the second derivative, just for future reference, would be 20x cubed minus 48x squared. All right. So after getting those, then let's go to, let's find the critical number, set derivative equal to 0. Common factor of x cubed. So that'd be 5x minus 16 equals 0. So that would mean, what do we got? X cubed equals 0, 5x minus 16 equals 0. Did I do that right? I think so. Okay. This one, of course, is just x equals 0. This one is, well, you add the 16 divided by 5. You got 16/5. Critical number there. Using the second derivative test, so let's just plug both those into the second derivative. However, we run into a slight problem. Very first one out of the box here, we get what? By plugging in the second derivative x to be 0, I've got what? 20 times 0 cubed minus 48 times 0 squared. What does that give you? Uh-oh, that gives you 0. What does the second derivative test tell you if your second derivative is 0? It doesn't tell you a thing. However, that doesn't mean it's not a local max or a local min. It just gives no information. So we're going to have to reboot, as they say, on that one. So we haven't found out about 0 yet. Let's see if it gives anything for 16/5. What is 16? Yeah, it's a pretty nice number, isn't it? 5 into that. Let's go with 3.2. Is that what 16/5 is? All right, so second derivative at 3.2 does give me some information, I think. This would be 20 times 3.2 cubed minus 48 times 3.2 squared. Well, that gives me something. It doesn't give me 0, I know that. 20 times 3.2 cubed minus 48 times 3.2 squared. That's 163.84. It's a positive. And so that would tell me concave, second derivative is concave up there. That's local min, isn't it? So f of 16/5, 3.2, whatever you want to call it, is a local min. So we get half the answer out of that. However, at 0, just have to go to the first derivative test, and that would just mean then break it up here. So you got 0, and then you got 3.2 out here. So just look on either side of 0, do your first derivative at -1 and the first derivative at +1, and see what those give you. At 1, we'd have, what, 5 times 1 is 5, 16, -16 times -1, so that'd be +16. That's +21, so that's increasing on that side. F prime of 1 would be it'd be 5 minus 16, so that'd be -11. So that's decrease. So I do have a maximum there, don't I? Increasing to decreasing, so that's a max. So so f of 0 by the first derivative test is a local max.